Everybody, my name is Takari Dimery and welcome to my Lab 3 of Physics 2211, the black hole. The purpose of this lab was to find the mass of the black hole by analyzing a star's orbit and to use this information to find the initial velocity your ship must have when it leaves the surface of the planet to fly around the black hole without crashing on the planet of the black hole. We used GlowScript to create a model of the star's motion and to extract the motion data and make our calculation loop. We will use Newton's second law of the momentum principle and Newton's universal law of gravitation. And the mass of my black hole was 7.39. Again, like I said on the last slide, some principles that we use were Newton's second law says that acceleration is equal to the net force on the object divided by its mass, and Newton's law of gravitation, which is given in the corner, says that on an object with a force on another object, which is based on the equation. You can see the code for the beginning of part 1, which is you can see the gravitational constant, which is g, the mass of the star, and delta t, which is the time interval between the points. Calculations. The code is formatted to make a calculation loop which calculated our parallel and perpendicular forces at many different intervals throughout the trajectory of the star. And so for the parallel and perpendicular forces, they were then combined to find the overall net force on the star at that specific moment. And then this allowed us to calculate the approximate mass of our black hole using the law of gravitation. In this code, we found P initial, P final, delta V, delta P, dpt, Fnet, and we also found Fnet and dpdt and Fnet and perp. So we did that we multiplied the star mass times V initial to find P initial and P final. And we also did delta P and delta P. So we did V final minus V initial, and then we did P final minus P initial. And so we did delta P over delta T to find F net. And so we calculated the parallel and the perpendicular also. And then we used Newton's second law to calculate F net for parallel and for perpendicular, as you can see below. And so for F net perpendicular, which is just equal to dp dt, and we just kind of renamed the variables. For part 2, we had to find the initial velocity of our spaceship, and these were our initial conditions given. So I plugged in the mass, we had the constant again, the mass of the planet, the mass of the ship, and then delta t, of course. And so the initial conditions for the planet were the planet's speed, the velocity, and that's how we do those. Also with our system and our surroundings. So our system was our spaceship, and our surroundings was the planet and our black hole. In my code below, you can see how this is the loop that we used, and as you can see, my rate is 5,000, which is very crazy. But I had to find R, and then I had to find R hat, and then we also had to find the force of gravity, and finally the distance from the ship to the black hole. So that's what all of this code means. So then we use Newton's second law, and we use the velocity update formula and the position update formula in order to basically make our ship move. And so we applied Newton's second law to make our planet and spaceship move, and then we added certain conditions in case of a crash. Well, they added conditions in case of a crash. This is the results of what my picture looked like, and my rate was 5,000, which was crazy because my planet and my spaceship was moving so freaking slow, and we'll talk about that in my errors. But this is my initial velocity and my closest distance from the black hole, spaceship, and the black hole. And I'll talk about why I don't have anything right there in the next slide. I had many errors in this lab. So for part 2 was really where I struggled, and I should have ran the program longer, but I also feel like it would have never connected, so that might be the case too. And also my initial velocity is mostly wrong, like seriously, because I did a guess and check method, so I feel like the whole lab could have been better overall. Thank you for coming to my TED Talk. Have a good day, guys.